CLI and a cross-platform IDE for C and C++. Download now.
Hello, hey everyone. Good morning, good afternoon, good evening, wherever you are. My name is Roi, and today I'm going to talk to you and hope to learn from you as well about structured concurrency and concurrency in general. So my name is Roi Barkan. In Hebrew, it's pronounced Roi. I live in Tel Aviv, in Israel. As you know, it's quite a strange time for being in Israel right now, but I'm happy to say that we have a good routine going, and there's a small chance that we'll have some, issues during the talk, but I'm sure that we'll get through them together. I've been doing C++ for quite a while now, and in the last 13 years or so, I've been working for Eastern Research. We're a low latency trading company based in Israel, and we're always happy to get more talents in our Israeli office. And I'm doing this conference thing and this meetup thing since COVID. I'm really enjoy it. I really encourage all of you to also participate right now here with me through the Q&A and gather time later on and submit talks, attend conferences. It's really cool and great. Here's the QR code for my slides. I'll also share a link on Discord later. Feel free to take a look. So today we'll talk about concurrency. We'll start with a relatively long introduction about what concurrency is, why people do it, what are current existing mechanisms or the main traditional mechanisms to perform and write concurrent systems in software. And then we'll spend a good portion of time discussing what structured concurrency is. In C++ 26, we're going to have two mechanisms for structured concurrency, and I'll discuss them, show little code samples, and give you some taste regarding how to use them, why to use them, etc. And then I'll spend the last portion of my talk trying to give you some advice and think together about ways to take existing code that is not using structured concurrency and migrating towards the structured concurrency paradigm. So concurrency is a relatively old thing, but when computers started to appear on the scene, like around the 60s and even 50s, everything was sequential. Okay, and what does sequential mean? We had an algorithm was just a set of commands, and the computer would perform one command after another. And basically, it was very certain that when an instruction started, all the predecessors are already complete, and every instruction could rely on the results of everything that came before it. But our environment, even then, was not so simple, where things worked in a sequential manner. First of all, things aren't sequential in terms of compute. Many times we don't have just a single processor running. We have multiple processors, and right now existing processors in most computers, they perform out-of-order processing, and they can perform their orders not exactly in the sequential order that they appear in. And we need to, if we have good compute, they can do things in parallel. We want to try and exploit that. The events that our systems work on, our inputs, they're also many times not sequential, and they're not built in a manner where all the input is ready before I start my program, and then my program can work on the input. Many times a system runs, and as it runs, new information arrives. It's not clear the exact order and the exact timing in which information arrives. And for that reason, when I write an online system, many times I need to think about this type of interdependency between the computation that I'm doing, the different inputs that arrive, and they might arrive in unexpected order, in unexpected sequencing. So sometimes those requests that are coming in can be related or linked to each other. And so, example, if the same person that works or the same customer of my system tries to check their account balance, and also they want to withdraw some funds from the balance, I need to make sure that the order that they operate with our system is the order in which my reactions also behave. And sometimes there are requests that are totally unrelated, like two different customers sending requests, and I can really treat them as if they without any consideration of which one do I handle first, and the sequencing of my handling of events doesn't have to be in any way connected with the sequencing when the events happened. And this is like a short nano banana illustration. Many inputs coming in, many threads on my system, and the ordering in which things happen doesn't have to be sequential. Things can be very, very messy. So that's what concurrency is when we're looking at systems. Let's think about a code a little bit, and how do we perform concurrency in code. So again, as mentioned, the main definition from my point of view for what concurrency is has to do with the dependencies between instructions and the dependencies between components. If two components do not depend on each other, then it doesn't really matter which of them runs first, and it's okay for the two components to run in parallel. But if they do depend on each other, you need to make sure that one does not start before all of its dependencies are ready. And there are several building blocks that currently exist in many frameworks to let us describe these types of dependencies. So one very, very simple mechanism is what's known as non-blocking APIs. And those are typically functions that I can call, and they're known to immediately return. They never block. And the thing is that if I ask the function to do something and it doesn't block, even if the action itself might take a long time. So for example, if I want to write some information onto the network or onto the disk with a non-blocking API, the function will return even before the actual write is complete. But someone or like the operating system will guarantee or will do its best so that the write will complete or the operation will complete in parallel to whatever I'm doing. Similarly, if I'm doing a non-blocking read operation, that means that if the data is already waiting for me, then the non-blocking operation will just give me that data. And if data is not available, the non-blocking API will just tell me that, hey, data is not available. Maybe you can try again later, or maybe it can get notified when data becomes available. So the notion of completion callback is one way for whatever subsystem, whatever operating system I'm working with to let me know when the actual work is done. Okay, and working with these completion callbacks sometimes is called continuation passing style, where I give the operating system or I give the framework some pointer or some lambda or some callback to which I want to be the continuation of the actual work that's going to happen asynchronously. And with this manner, I just ask the infrastructure, hey, do this thing asynchronously, return the control to me as quickly as possible. But once the actual operation is done, this is what I want to continue with. This is my continuation. Another approach for non-blocking APIs is to give some identifiers that represent the result instead of the results. And using these identifiers, I can later go on and check are the results ready, or what's the status of the operation. These identifiers are sometimes called futures. Okay, and so the framework will have a promise that they need to deliver to me, and the future is something that me as a user can have, and I can check whether or when the promise is fulfilled. Another building block that's common is the notion of a fork. And when I say fork here, I don't just mean the POSIX operating system call. I mean really the conceptual notion of taking one thread of instructions and splitting it into two. Okay, so a fork operation is a non-blocking API that can perform any arbitrary function or any arbitrary piece of code in parallel or concurrently with whatever I'm doing. So I call fork, I give it some continuation or some piece of work to do. Fork immediately returns, I can continue with my business or whatever I want, and the framework will guarantee or do its best for that extra piece of code to happen concurrently with me. And again, I'm not talking just about the operating system called fork, but this is like an entire notion. In C++, stud::j thread and stud::async are examples of calls that perform this type of fork operation. And the counterpart of a fork is a join. And the join is a place where I can take, again, an identifier of some work that I schedule to work asynchronously, and I wait for it to complete. I do not want to continue my own thread of instructions before another thread of instructions is complete. Okay, and this is what creates a dependency or dependence. Another building block that many times is used are things like mutexes, semaphores, barriers, etc. These are, I guess, more fine-grained ways in which several threads of operation that run in parallel can synchronize between just parts of themselves, or create these dependencies that are not full dependencies that wait for one task to complete before I start another, but let two tasks run in parallel, but still have some level of synchronization among them. And cancellation is one last piece of our toolbox that sometimes happens, which is a way for me to let the system know, or let the infrastructure know, that some extra work or some asynchronous operation that perhaps is not even complete yet, or maybe even hasn't started, is something that I do not wish to spend time on. I do not plan to depend on it. There's no reason to do it. And so that's a signaling mechanism that exists. In C++ 20, we've got stud : stop source and stud : stop token as the first way or first mechanism in our language to convey this notion of cancellation and the desire to cancel some asynchronous operation that might be in flight. Okay, so again, some chart with all these building blocks. I can create like these nice dependency graphs that describe different tasks that need to run and different dependencies among them. And if I describe the correct graph, then whatever infrastructure or operating system that I'm working in will make sure that no task will start before all of its dependencies are ready, etc., etc. Okay, so we have this mechanism. We talked about it. We know how to use it. But what's the point? Why would I write a concurrent system? And there are several reasons. One main reason is to exploit parallelism. Okay, it's very common that an existing computer system has a lot of units that can work in parallel. So we can have multiple processors, we can have GPUs, we can have several other types of peripherals like hard drives, external peripherals. We can have networking gear, etc. And all of them can potentially work in parallel. And they don't. So if I tell the system, hey, these operations do not depend on each other, and I allow the system to run them in parallel, I can get a chance to exploit that parallelism. A second motivation is separation of concerns. Sometimes I have several parts of my system that don't really depend on each other, and I want to try and develop each of them separately. And I also want to develop the mechanism that decides what to run when, or to schedule them, who also do that separately. So I can independently develop different components within a system, like different processes in a Linux environment or in an operating system, or maybe different threads that handle different requests from different types of customers. And I can have a different person or a different team in charge of dealing with the priorities, the fairness, the scheduling apparatus that basically decides how do we map all the different instructions and components that need to run in parallel onto the different resources, like processing resources, network resources, etc., that are available on the system. So some teams can independently develop different types of components that might run in parallel. Another team can specifically focus on how to map those processes into resources, how to deal with priorities, fairness, etc. Another potential motivation to write a concurrent system is to perform some hiding of tail latencies. Sometimes if I want to complete a certain task, I can have several different ways of achieving that completion. I can maybe either do a long computation by myself, or I can look it up that information in my disk, or I can go and fetch that over the network. And if I have a mechanism that is concurrent and allows me to run all these different approaches in parallel and do sort of a race where the fastest one wins and cancels all the rest, it can guarantee that whatever the system state is, whatever the bottlenecks might be, I give the best latency towards my customer, towards whoever sent me the request. And once one of the different approaches is complete, I can just cancel the rest, and I get maybe spend some extra resources in the meantime, but make sure that my latency is optimal. One more motivation is just doing efficient batching or chunking. Sometimes my system receives many events in a short amount of time, and I know that dealing with them one by one can be less efficient than batching several related events into one batch and dealing with all of it together. This many times when the load is high, this can really help. If some of you have heard of something called the elevator algorithm that is implemented many times by rotating disk manufacturers in order to deal with many hard disk read requests or write requests that might need to access very different areas in the hard drive. And those are the types of exploitations or efficiencies that I'm talking about, where I can look at the entire set or batch of requests coming into the hard drive, and I can order them, sort them, and manage them together as a single batch and get some extra efficiencies. And this is like a short illustration of what a race looks like. When again, trying to run different requests, and if the database is ready first, then I can cancel everything else, and no need to get to the timeout finish line, etc. Okay, I hope this is all understood. And now we've talked about the building blocks, we talked about why to do it, and then there are several techniques or several ways to architect a system where that is concurrent. And so we're going up into the architecture or system architecture level. One very common and very relatively simple way to do it is to use the operating system threads or processes. Okay, so an operating system is typically a very robust component that's shipped by very few vendors that are very well trusted, like Windows, Linux, Mac OS, etc., or Android. And one of the key mechanisms or key guarantees that operating systems support is the notion of multiple threads or multiple processes running together. The operating systems have very good schedulers, and they can deal with scheduling, preemption, context switches, interaction with hardware, etc. And so if I set up a system where I have many threads or many processes that seem to run sequentially, but I let them all operate within a single on a single server with a single operating system, and the operating system basically gives me all the concurrency facilities that I need. And whenever a processor, for example, is invoking what looks like a blocking API towards the disk, the operating system makes sure that the CPU is not really blocked, but actually a context switch happens. The CPU maybe caters to another process, and once the data arrives from the disk, that's when a different context switch will come back and join and give my process that was blocked on disk the processor back so that I can run with it. The main advantages of using an operating system for concurrency is that it's very simple. In C++11, we got the ability to, in a standard fashion, to run threads, and since then it has been very easy to write concurrent applications in C++. The main drawbacks of using the operating system for concurrency is that there's a relatively high overhead and little control. Operating systems, they have to be very generic. They have to assume nothing about the different processes or threads that are running. So they have to they have a very difficult task of dealing with fairness, dealing with potentially runaway tasks that want to consume all of the resources of the system. They need to deal with permissions, and when I start my own system or my own program running in C++ using threads, I typically have very little control over the scheduler of the operating system, and in ways of telling it how exactly I want it to behave. And then the second mechanism that can be available for us to architect our system with is using virtual threads. These are sometimes called also green threads or user threads or stackable coroutines or fibers. These are actually a little bit of a higher level mechanism than operating system threads, but they're very, very similar. The idea is that we have multiple stacks for our logical threads of operation, but they are all managed within a single process, within a single framework, up one level above the operating system. And because we're one level above the operating system, we can be much more lightweight. We can be we can switch much more easily between different threads or virtual threads within our system. But the main drawback is that those mechanisms or those frameworks typically are cooperative. And cooperative means that once I give one virtual thread control of the CPU, they will use it, and it's up to them to give the control back to the framework. Okay, and if they try to hog a virtual thread, typically there's no preemption mechanism in these settings. So again, the pros is that the coding style is very, very simple to operating system threads, but the overhead is lower, so relatively easy to write, relatively low overhead. The main disadvantages are that there's no standard support for these types of threads in C++ yet, and the overhead is not zero. Again, for every different virtual thread needs to have its own stack allocated, and the whole scheduling and switching is not zero overhead. And I have a feeling that this is the main reason why C++ standard does not yet have any standard mechanism to do virtual threads. And then a third approach is what's known as a reactor or proactor thread, or reactor-proactor thread pools. In this approach, basically we have very, very generic single-threaded engines that are very, very generic, and they handle short non-blocking tasks. Okay, so with this approach, I take the work that I have to do, I split it into many, many tasks, where each task is non-blocking by itself. And the reactor threads or proactor threads, they receive tasks in a generic way and perform them one by one, knowing that there's nothing should be blocking. All the tasks should be non-blocking, and that way I can get a very, very high performance, very, very high throughput, very, very quickly, and utilize all my resources. So the pros is that the overhead of reactors is very, very low. There's no operating system required. And frequently, because there's maybe only one thread or only a single thread that performs a single type of operation, I don't even need any mutexes or anything like that, because I know that different concurrent pieces of work that are split into non-blocking tasks, I can know that a specific type of task will only be one instance of each specific type of task will be running at any point in time. So I don't need to try and synchronize with other tasks of the same manner. The main downsides of the reactor or proactor model is that it's relatively complicated to implement. Taking work that naturally has both a lot of computation, a lot of I/O, a lot of inherent complexity, and breaking it down into several non-blocking tasks is not trivial. It's relatively complex, and this, if we want these high-performance systems, then a lot of this burden lies on us, the developers. So these are three main techniques that existed and were very, very prevalent in the software world until about 5 or 6 years. And I think around that time, and the new paradigm of structured concurrency came along. And in order to talk about that, I'll also dive a little bit into what ways do we have to take our work and split it into several tasks. Okay, so one way to write or implement a mechanism where I take a very, very complicated piece of work and split it into tasks is what's known as a state machine. Okay, in the state machine, I can basically have different states representing pieces of non-blocking work, and the edges or the transitions between states, they represent the blocking operations or the asynchronous operations that need to be done before moving on from one piece of work to the next. Okay, so if I implement my code as a state machine and each state itself is independent and non-blocking, I can relatively easily put those state machines inside a reactor model and let those reactor threads try to see which state machine is currently ready to be executed, execute the current state, which might invoke some asynchronous operation, and then put that state machine back into some queue until the result is ready and we can transition to the next state. Okay, this is very, very suitable for example for multi-state protocol implementations like TCP handshakes, like SSH protocol, various places where it's relatively known and very documented how and when things move from one state to another. And as the state chart becomes more and more complicated, or if there's more and more like dependencies or flows that somehow need to coordinate between different state machines that live in parallel, that's when things become tricky, and we find systems that rely on state machines to be more and more convoluted and complex. And again, the typical way the code will look like if I'm using state machines is that the reactor will have some kind of a lookup map, or like an unordered map between like a request that's being handled and its current state machine with its current state. And whenever whenever a state completes, it will tell the main thread or the reactor what is the async operation that needs to be done before waking the state machine up again and on which state, and that's how these things will work. Another mechanism that's typically used, and it's relatively common in other programming languages, is what's known as callbacks or continuation passing style. And again, in that mode, the tasks themselves, they run async operations that complete very, very quickly and supply each async operation with the callback for completion, with the continuation. And again, the reactor thread will know to run those completions whenever the work is done. This is also the mechanism in which Boost ASIO library works. I assume some of you might have heard of that library, and we'll see an example later on. And it really fits well with, since C++11, with C++11 lambdas and with stud : functions as a relatively easy and inline way to stick some code of the completion or the continuation very, very close to the code that invoked the async operations. And again, we'll see an example in the next slides. The tricky part with the continuation passing style and callbacks is managing object lifetimes. As you know, C++ is very keen on resource management. The main mechanism for managing resources in C++ is the destructors and the scopes of stacks and function completions, etc. Once you start passing objects around and pointers around with callbacks, managing lifetimes can become tricky. And the last mechanism that can exist to help us take a large piece of work and split it into tasks is what's known as structured concurrency. And again, it's meant to be, it came into the scene, I think, about 5 or 6 years ago. And I think not the first structured concurrency implementations that I've seen in the industry were in other programming languages. And now with C++20 and C++26, we have some structured concurrency mechanisms at our disposal, and this mechanism or this method is supposed to be better than callbacks and continuation passing styles and even state machines, because they let us write code in that can be very, very efficient but also expressive, and we'll see examples very soon. So this is a code snippet that has to do with that's written with the Boost ASIO library. In this code snippet, we can see that we're actually writing some class that wants to perform an echo operation. Whenever new data arrives on some socket, I want to read it and write it back to whoever wrote it to me. And whenever new information, whenever I write information, then I want to start reading back again when the write is complete. So So this is an example piece of code. Let's try and dig a little into it and see what goes on. So we can see we have a class that has two main members, or actually one is a socket for communication with another side of the protocol, and the other is a data buffer of some existing length. And the start function calls doRead. And if we look at it, we see that doRead operation seems as if it calls doWrite, and the doWrite operation seems as though it calls doRead. So if it looks like some kind of a recursion, and one might think, hey, this can lead to Stack Overflow, doesn't it? But the trick here is that this isn't what happens, because these calls from doRead to doWrite and the other way around happen within a lambda, okay? And this lambda is actually passed into the ASIO framework, and the doRead operation actually returns very, very quickly without calling doWrite. Our framework will call doWrite once the read operation is over as a continuation. And that is what lets us avoid a Stack Overflow, and that's what lets this whole mechanism write and work concurrently. I will say that because there is no stack here, it's very, very important that the object itself that is created will not get destroyed, and will know to live just for the right amount of time and until the entire communication path is over. And for that reason, we use shared pointers. Okay, we use the shared from this idiom to make sure that our own session is created on the heap using a shared pointer. And before doRead is complete, it makes sure to give this shared pointer to itself into the ASIO framework. And this is what ensures that it will be okay to call doWrite on this object once the read operation is complete. If I had not given this self object to the framework, there could have been a risk that this pointer will actually point to a dangling location, because something else could have deleted my object, and the call to the lambda might try to run do while on a dangling pointer. Okay, so this self is key, and this notion of shared pointers to as a mechanism to make sure that whenever our callbacks or continuations are still alive within the ASIO framework, the objects that need to respond to them are also still alive. Okay, and as I wrote here, if I set up this async stuff and then write some more code here inside doRead, this is probably a bug. And what I mean is that I need to understand that whatever happens here will not happen after the write operation or after the read operation is complete. It will happen right after the async operation is done, very, very soon after I invoked the asynchronous concurrent action. Okay, so that's a continuation pacing style. And again, the main complexity here is that I need to manage lifetimes. And if I squinted it, it looks as if one function calls another, but we understand that it's not really the way that it works. So now let's switch gears and talk about this new paradigm called structured concurrency, what it means, and how we can write our own code and benefit from this paradigm. So let's see if there are any questions. I don't think I see questions. Great. So the philosophy behind structured concurrency is that is one that tasks are resources in the same manner that RAII discusses resources. Okay, so RAII, if you recall, is resource acquisition is initialization, and much more importantly, resource destruction is deallocation. So with RAII, we know that whenever an object comes out of scope, we can release all of its resources. And structured concurrency basically tells us the tasks that we need to work on are resources just like any other resource. And we want to use RAII, we want to make sure and create some link between the lifetime of the task and the lifetimes of objects, and makes use of different C++ scopes and other mechanisms in order to make sure and maintain those types of resources. So every task belongs to a scope. And if a task has subtasks, and then they typically belong to a subscope of that task. And the main thing is that every scope will not be destroyed before all the tasks that belong to it are complete. Okay, so the structure of a scope will make sure that all the tasks belonging to that scope are already complete. It might wait for them to complete. It might signal to cancel them. But even if it signals a cancellation, it will make sure that the cancellation actually happened before they get destructed. Okay, so we basically create some link between a scope and potentially like other objects and memory resources and the actual tasks that reside within those scopes. And we cannot simply just spawn tasks out of the blue that can run away without belonging to any scope. And an analogy to think about is like the difference between stud : jthread and stud : thread. I'm not sure how many of you are familiar with it, but stud : thread typically can be destructed, and while the actual physical thread is still running, while with jthread it's much less meant to work that way, and jthreads typically will not be destructed until the physical thread is done and complete. And the main advantages of writing our code in the structured concurrency philosophy is that, again, we can use the ending curly brace as like a symbol of power. Whenever we see that end curly brace, we understand that this is something that is going to do cleanup. This is something that is going to wait. We look for these curly braces as a way to understand and envision how an entire tree of a concurrent operation is going to run, what is going to exists at what point in time, what is going to be destructed, etc. And then I know that every end curly brace means that every task belonging to it will be completed. So I know that everything and belonging to the scope can be deleted, etc. And similar to C++ objects, I don't have to let all the tasks complete. I can also return them like stud : mover, or like copy lesion operation back to a higher scope. But that's typically less common. And again, still every task will still belong to a scope, and if it outlives the scope that it belongs to, it actually or it's only because during the destruction of that scope, a task sort of like migrated to its parent. And this makes our entire work tree and our entire algorithm very, very hierarchical and very, very composable. Okay, whenever I look at a tree-like structure like this of different tasks, one within another, I really know that I don't really care about the specifics of the very fine-grained details if I want to look at the entire graph at a high level. And if I dive deep into one specific branch of the tree, I know that no other branch of the tree might collude or hurt me. Okay, again, if I go back one slide, we can see this nice illustration by Ben Weidig. You can see that every task can have subtasks and more subtasks, etc., like in a recursive manner, everything very, very composable. Okay, so that's the philosophy and the advantages. And once we have this mechanism, it's much more intuitive to deal with errors, deal with cleanups, and deal with cancellations, because it's very, very clear which task and which piece of works belongs to which which scope. And if I want to cancel one thing, I know who are its children, which task is its parent, etc. So one interesting observation is that typically coroutines written with the co-await keyword are structured concurrency. What do I mean? I assume many of you know of coroutines added and introduced in C++20. Basically, when a coroutine gets created, there's an allocation in the heap typically of a coroutine frame, some piece of resources, some memory resource that can live throughout the lifetime of the coroutine itself. And a return object is also created. And then whenever inside the coroutine I perform co-await, the coroutine gets suspended, and all the state gets kept on the heap inside the coroutine frame until, and even the awaiter itself that represents the work that's being done that we're waiting for, It's all within the coroutine frame, and none of it will get destroyed until the work that I'm waiting for will be complete, or until destruction happens or cancellation happens across the board to the coroutine frame and all the awaiters themselves. So if I have a suspended coroutine, and in the frame I have several awaiters that represent subtasks, then I can consider this coroutine frame as a scope, and the subtasks living inside awaiters, they create these subscopes. And again, once a task is suspended, the coroutine can be resumed or destroyed, and both of them involve the awaiter, which means that both, in the case that I get resumed or that I get destroyed, this is like an entirely hierarchical thing, entirely composable thing. If I act on the parent coroutine, all the children gets acted upon together. So the awaiter object is a link between a parent coroutine and child coroutines. This is the link that creates this notion of structuredness within coroutines between a task and its subtasks. And the structure of a coroutine frame basically will make sure, we'll call the structure of the awaiter, and the awaiter being destructed can very easily cancel or notify cancellation of the subtasks. And this is what will give us this notion of philosophical notion of structured concurrency. And await resume is that operation that happens. It links the child tasks back into the parent, and they can do error propagation and deal with successful completion as well, as a way of making sure that once a subtask is complete, the parent task knows exactly where to move off of. And I should note that although the co-await keyword seems to imply that a single coroutine can only create one subtask, this is not the case. With coroutines, we can also create one-to-many relationships where a single coroutine can co-await several awaiters at once by simply composing the different awaitables. Even in the ASIO library, which supports coroutines, it has experimental operator ampersand and operator OR that does this type of composition very, very seamlessly. I don't know if you've seen this CPPCon 2022 talk by Danielle Engert. I really recommend it. And as part of the talk, she also discusses this OR operator, which lets her and people create these types of races between two different asynchronous operations. So here we have a result that co-awaits two different async operations, async read and some async wait, with an OR between them. And this is a race. Okay, so the first one that's done will basically send a cancellation request to the other one, and the result will typically be like a variant of one of the two. Okay. So that was coroutines, and I hope that convinced you that coroutines are structured concurrency. Now let's talk about senders. Senders and the student execution library are new to cplusplus. We're just about to have it, and they are also key to the notion of structured concurrency. So I assume some of you don't know what senders are. So basically senders, they are just, it's a concept, a cplusplus, a concept that represents some type of asynchronous computation that needs to be done with multiple potential results. Some results can be success results, others can be error results or cancellations. And the core operation that people can do with senders is the composition. Okay, so if I have several senders, I can compose them into computation graphs that are more and more complex with various sender adapters, and those graphs are sort of like expression templates that give me a representation of an entire algorithm that's split up into different components, each of which is non-blocking. So sender adapters, they are the mechanism that connect different senders together into one big structure, and they guarantee the structured concurrency philosophy. They make sure that whenever I link two different senders as where one is a subtask of the other, then the philosophy will be adhered to. And similar to range adapters, again, we're creating these onion objects where if I compose different senders into one big object, then you can inspect the object and look at it. And it's like a large template that composes of everything else, like an onion with different layers describing the layers of computation. And once I start the work, the asynchronous work, then that onion gets peeled one layer over another. So with regards to the differences between senders and coroutines, I would say that the senders are more bare bones than coroutines and are more capable. So in a sense, it's a more direct way to interact with like existing third-party frameworks like hardware mechanisms, like operating system mechanisms, etc. They're more close to the bare metal with less need for waitables, less need for heap allocations for coroutine frames, etc. They give us a lot more control over memory layout. There's no need for endlessly or needlessly wasting your resources. But on the other hand, it might be a little more complicated, at least at first, to write complex or elaborated algorithms using the sender. And again, the key insight that we also remember is that the C++ standard made it very, very clear that senders are actually awaitables and awaitables are senders. So the standard made it such that whenever I have a concurrent system that uses coroutines and awaitables, I can compose such a system with the sender framework, and the other way around. If I have like sender algorithms and I want to add some more capabilities using awaitables and coroutines, it's also possible. Because a sender is an awaitable and an awaitable is a sender. And here's a little bit like a screenshot from a good talk by Bryce Edelstein-Leibach from CPP Now 2022, when he basically describes this notion of the onion, where if I have an operation followed by the function f followed by an extra operation, then a sender will be sort of like an onion, knowing that that if I look at it from the outside, all I can see is the result of the after operation. But I know that if I want it to complete, I need to wait for the before operation to complete, and that's done by peeling the first layer of the receiver. Then I need the F operation to complete, and that will be done by peeling the second layer of the receiver, and only then the after part will start. And once that after part is complete, that's when I can see the result of this sender that represents the entire chain of operations. Okay, and again, this layer and these layers, an onion, really lend themselves and look much like what we've seen with structured concurrency, where each task belongs to a scope that belongs to a different task, and we have subtasks here, etc., etc. Okay, so let's look at a few code examples again of coroutines and senders and try to compare and contrast between them. So here's a read function that is implemented using coroutines. Okay, so let's see, it's implemented using coroutines. The return value is an awaitable of void, and the function itself, has a co-await. And what does it do? The function receives a socket and a span to which we want to fill information in, and we run in a while loop, and as long as we haven't filled up the entire span, and with each iteration we'll use the ASIO library to read some information into the span. The co-await, and once it returns, I can see how many bytes arrived. If 0 bytes arrived, I know that it's the end of file, and I didn't expect it, so I'll throw an exception. And if bytes did arrive, I can move and shorten my span into a subspan of whatever's remaining. And if what's remaining is not empty, I'll go into the next iteration, and on and on and on. And again, we can see that this looks like a loop, but actually in each and every iteration, we stop our computation, get suspended, and we will get resumed exactly at the point where we got suspended once some information is available in the span, and the bytes array tells us how much is that. Okay, so that's an implementation of structured concurrency using coroutines. Now let's look at this exact same algorithm, courtesy of Robert Lee, that works using senders and receivers. So first of all, we can see that the code is a little longer, and I imagine that it will be less intuitive for many of you who aren't used to it to read it. But the key token to look at in these in this function is the pipe operator. Okay, the pipe operator, similar to range adapters, are sender adapters here, and they're the ways in which we compose different chunks of work into one big task or algorithm. So let's see what's going on. We have a function that receives a span and needs to fill it with information. The return value is a sender. And what is that sender? We start off by moving the span from the regular world into the async world using the just algorithm. And then we add a continuation. That value will add a continuation that starts the work. And the work that I'll do is basically a repeat until the span is empty. Okay, so this repeat until is very, very similar to the while loop that we have here. Okay. And what are we going to do in each iteration? Again, another sender composition of sender of the subtasks. So again, we'll start with nothing. And in each iteration, I start with nothing. I perform a read operation. I know that once the read is complete, I can attach on a continuation that accepts the number of bytes, and then I can convert the span into the subspan with whatever bytes are remaining. So that's the basic idea of what's going on here. Again, we can see that this is sort of like we can see the onion being created in here. It's very, very different than looking at the for loop here. But the cool part here is that there are no memory allocations that I do not see. Okay. One thing to notice in both cases is that the return value or the return, when we return both from the read operation here, or when a read object or waitable is created, then nothing is started yet, right? Work only starts once the coroutine gets resumed, or someone tries to turn on or to wait for the sender result. And for that reason, both coroutines and sender algorithms typically receive their arguments by value and not by reference. And typically they need to, again, deal with that value and make sure that it doesn't get destroyed. It will typically live inside the onion in this case, or it will live as inside the coroutine frame in the coroutine case. Okay, so we take our arguments by value, not by reference, because the lifetime of this code is much longer than the lifetime of those arguments. Okay, I hope this makes sense. And now we've covered like the vast majority of our talk. So this is a good time for a short summary and to get your questions. So again, concurrent systems are ones that can handle complicated scenarios of many incoming events in different orders. We can achieve a very, very good performance by eliminating helper facilities like threads, stacks, and heap allocations. The older approaches that existed are relatively error-prone or complex, required a lot of attention to detail to make sure that things don't get lost. We need to manage object lifetimes, handle complex scenarios, deal ourselves with errors and cancellations. And structured concurrency is a relatively new but relatively stable and battle-tested framework for writing composable, low-overhead algorithms. And again, both coroutines and senders are implementations or ways to write structured concurrency code. And the cool thing is that they also can interoperate between each other. Okay. So I have just a few more minutes to try and give you some tips about how to take a concurrent system that doesn't use structured concurrency and migrate towards structured concurrency. I'm relatively happy that I don't have many minutes left because I don't have many tips to give you, but still. First of all, first tip is that although this is new to C++ standard, all these frameworks, they exist and have relatively good production grade libraries in the wild that you can use. Okay, so if you want to take an existing system and migrate into structured concurrency, try to look for existing libraries and don't start from scratch. ASIO, I've shown you examples, is a very good and battle-tested one for typically for operating system and network interaction. CPP Coro gives a lot of building blocks for implementing coroutines. Cobalt is another coroutine library with ASIO compatibility that's part of the Boost library as well. StudExec by NVIDIA is, I think, the most mature senders library that exists for like server infrastructures like Windows or Linux or even like operating system-based infrastructures. Beam and execution is the first like example implementation that's meant to go and be as standards compliant as possible. So if you want to prepare for C++26, go and look at Beam and execution. And Beam and Net is something that aims for C++29 standardization of implementing senders for networking capabilities. That's my first tip. Secondly, try to keep control of your own main loop as much as possible. Okay, so many frameworks or mechanisms, they want you to do some setup inside your main loop and then call like one main function that never returns. And that way you lose all control of your main function. And this is relatively harsh because there's no gradual migration from an existing system that doesn't use it all the way to something like that. But in many cases, you need to remember that you don't have to relinquish control of your main loop. For example, even inside ASIO, the IO context object, which is the notorious main loop or scheduler, it has a : poll method for non-blocking task draining. And this way, I can, with this and with these types of mechanism, I can implement things that are part coroutine in part non-coroutine, or part ASIO and part non-ASIO, or part structured and part non-structured. So use that, keep control of your main loop as much as possible in order to work in a gradual fashion. And where should you start? If you already have a system that is composed of many different tasks, where can you even start? So I would first suggest that you try coroutines first and not senders. Coroutines are already standard. There's a lot of libraries that exist that handle coroutines, so I really encourage you to start with that. And we need to remind ourselves that if we start with coroutines, moving towards senders will not be a big issue because they are meant to interoperate. Secondly, if your current code is already a reactor with non-blocking subcomponents or non-blocking tasks, consider starting from the root and not the leaves. So take the root function that basically is already non-blocking and just invokes a single task at a time, and change its returns to core returns. Okay, and this way you suddenly your main function or your root function becomes a coroutine, even if it doesn't co-await at all. It's a coroutine, and you can integrate it into your framework where each call doesn't block. And then you can start sprinkling co-await in places where things seem to make sense. And whenever a co-await gets entered into the root, it means that the root will not complete whenever it's run. It will get suspended, but again, your framework will know how to deal with it in a gradual manner. If your current code is blocking, like using threads, etc., and you want to move towards structured concurrency, then I would recommend to start from the leaves. So take a few small tasks that are are relatively at the bottom of the chain, they have no dependencies, and convert them into coroutines, and then migrate up towards the root one by one. And the reason for that is what's known as the function coloring problem. If once I take a function that is not a coroutine and I turn it into a coroutine, everything it depends on has to also become a coroutine. So it can be very viral. And that's why I would start at the leaves and not at the root. And don't fear the notion of cancellation. Okay, so both kinds of structured concurrency, it's totally okay to take a piece of work that hasn't completed yet and cancel it. This is not something to be afraid of, like in the non-structured concurrency way. And this is sometimes a very good mechanism to take existing code. And you're not sure exactly how to make it structured concurrent because something might outlast some work might outlast the work that I'm doing on, and I'm not sure how to deal with it. So I can just do cancellation. That's sometimes a way that can help me. Some will need to interact with the suspended coroutine. You can just cancel that suspended coroutine and start afresh or something like that. And you can also be creative with the return type of co-await. Maybe co-await can return to the expected. In this way, sometimes if the suspended coroutine is ready or not, I can have to do some tricks there. Okay, so about 1 minute to go. So time for a summary slide. So again, structured concurrency is a paradigm shift. Let's see, no questions. Yeah, is a paradigm shift for me and for many of us. If it's used correctly, the promise is that it will give us a more reliable code, more safety, and very, very little overhead. And we can control the amount of overhead, whether we use coroutines or senders and receivers. As of 2026, we'll have two mechanisms, as I mentioned. The coroutines are still relying on some third-party helper libraries. There's even in C++26, we don't yet, I think, have like a good type erase the task type, etc. But we can use third parties, and centers are fresh out of the box. Again, expect more libraries to come. And now is a good time to start our preparations and migrations. Now is a good time to take in our systems that are not yet structured concurrent, that are not yet in C++20 or 26, and try to understand how to change our architecture, how to move towards structured concurrency, and where it might help us. So thank you very much. I hope you enjoyed the content, and I'm very, very happy to get questions, probably already in GatherTown. So thanks a lot. I also, by the way, have some extra slides, bonus slides that I might show in GatherTime if you like, for more details. So thanks a lot.